Alright, so we're going to be talking about primes and divisibility in this pre-lecture video. So for two integers d and n, we say that d divides n if there's an integer k such that n equals kd. And then our notation for this is d and then this vertical bar n. An equivalent definition for d dividing n is that d divides n if and only if n divided by d is an integer. So this is what we would usually think about as d divides n, but it turns out that that first definition that I give here, so this one here, that one is actually more easier to work with for proofs. So that's what we're typically going to use, even though the second one is more consistent with our intuition for divisibility based on what we learned in earlier math classes or growing up talking about divisibility. So for example, 2 divides 10. Since 2 times 5 equals 10, there 5 is that integer k here. 6 divides 12, since 6 times 2 equals 12. 3 does not divide 8, so this notation here means does not divide, so we just put a little cross there through that vertical line to mean not, so that means does not divide. And the order here is very important. So we have 2 divides n, but 10 does not divide 2, since there's no integer that we can multiply by 10 to get 2. So it's really important to pay attention to the order here, that it's the first one dividing the second one. And similarly, 12 does not divide 6. So for an example of how we can use this definition to prove things about divisibility, if A divides B and B divides C, then A divides C. So if we have A divides B, that means there is an integer k such that k a equals b, and when we have b divides c, that means there is an integer, and we'll call this one L since we don't want to reuse k there, such that L times b equals c. So then to say that a divides c, we want to show that there's some integer that we can multiply by a to get c. So what we're going to do is start with c. So we've got c, and since we've got our lb equals c there, we can write c as L times b. And now we've also got that b equals ka. So we're going to replace b with that, so we've got lka here. And then if we regroup this, so we've got lk times a, we've got some integer times a equals c. So a divides c. So here lk is an integer, since it's the product of two integers. So that's how we can use that definition of divisibility to prove things about divisibility, and that's easier than working from our kind of more obvious, the definition that we learned growing up. So another example of how we can use this to prove things, if d divides x and d divides y, then for any integers a and b, we have d divides ax plus by. So d divides x, so that means there is an integer k such that k times d equals x, and d divides y, that means there is an integer L we'll use such that L times D equals Y. And now we want to show that D divides AX plus BY. So similar to the last proof, we're going to start with AX plus BY and figure out how to write this as something times some integer times D. So we've got AX plus BY. We know that X equals KD, so we can make that replacement here, A times KD. And we also know that Y is LD, so we'll make that replacement in the second part here. So we've got BLD there. So now we're going to regroup this. We've got AK times D plus BL times D. So then factoring this, we've got AK plus BL times D, and AK plus BL is an integer. So D divides AX plus BY. So we say that a divisor is D of n is proper if it's neither plus or minus n nor plus or minus 1. So for example, 6 is a proper divisor of 12 since it's neither plus or minus 1 nor plus or minus 12 and it divides 12. A positive integer p is prime if it has no proper divisors and it's bigger than 1. So 1 is not prime, important to remember that. 7 is prime since its only divisors are plus or minus 1 and plus or minus 7. 41 is prime. 27 is not prime, even though that's an easy mistake to make. That's a common thing that people forget, that 3 divides that, or that's 3 cubed. So just looking for things that have no proper divisors. We've got this kind of slick test for being able to tell if an integer n is prime. So a positive integer n is prime if and only if it is not divisible by any of the integers d with 1 less than d less than or equal to square root of n. So in order to check if something is prime, we actually only need to check for divisors up to the square root of that number, rather than checking everything less than the number. So notice that this statement is if and only if here. So that means we've got 2 directions to prove here. So first of all, in the forward direction, we're assuming that n is prime. So assume n is prime is our starting point there, and we want to show that it's not divisible by any of the integers d with 1 less than d less than or equal to n. So n is prime. That means that n has no proper divisors. So certainly it can't be divisible by any of those d between 1 and square root of n, since that would give a proper divisor. So then we've proved that direction, so now we're going for the other direction. So we want to assume n is not divisible by any of the integers d with 1 less than d is less than or equal to n. So we want to show that the integer n has to be prime then. So let's suppose we've got some divisor of n. So let's suppose a, let's say, is a divisor of n. So we want to show that n has no proper divisors, so we want to show that ultimately a has to be plus or minus 1 or plus or minus n. So a being a divisor of n, that means that there is an integer k such that a k equals n. So now if a is negative, then minus a, or the positive version of a, is also going to be a divisor of n. So we can actually take a to be a positive divisor, and that won't change anything here. So we'll take a is a positive divisor. And now we're assuming that n is not divisible by any of the integers d with 1 less than d is less than or equal to n. So since a divides n, that means that a is going to have to be equal to 1 or a is bigger than root n. And the same thing is true for k. So since k divides n, k has to be 1 or k is bigger than root n. So let's look at these cases here. So if a equals 1, then that one's okay because it's not a proper divisor. If k equals 1, then we've got a times 1 equals n. So a times 1 equals n implies that a equals n, so it's not a proper divisor. So now we're looking at the case where both a is bigger than root n and k is bigger than root n. Then when we multiply those together, a times k is bigger than root n times root n equals root n. But wait a minute, ak is supposed to be equal to n, so that means this is a contradiction. So since this case led to a contradiction, this isn't possible, and these first two are the only possible cases. So that means that a can't be a proper divisor. Since in both of the only two cases that it worked, a was not a proper divisor. So since we started with any divisor for n, n has no proper divisors, and n is prime. Squeeze that in there. Alright, so then we've proved both directions of this, so showing that a positive integer n is prime if and only if it's not divisible by any of the integers d with 1 less than d less than or equal to n, square root of n. So we've got a easier test for prime numbers than checking everything less than the number we want to know if it's prime. So the greatest common divisor of two integers a and b is the largest integer d that divides both of them. So d divides a and d divides b. So a theorem is that for any two integers a and b, the greatest common divisor of those integers always exists. You can read a proof of this in the book. The least common multiple of two integers a and b is the smallest positive integer m, such that a divides m and b divides m. So it's the smallest thing that's a multiple of both a and b, or that both a and b divide. So this also exists for any integers a and b, and that proof is also in the book if you'd like to read that. So these proofs where I'm just referring you to the book. The reason that I'm doing this is these are the sorts of proofs that I wouldn't necessarily expect you to be able to come up with on your own, so I'd rather not put the emphasis there. But if you're someone who's considering going to grad school in math, or you're a math major doing lots of proof-based math classes, being familiar with these kinds of proofs is a useful practice and a useful thing to do. So I'd suggest working through those proofs and making sure you understand them if those are your goals. Otherwise, I would suggest focusing on the sort of shorter proofs that I would actually be asking you to do in group work, in homework, on the quiz, on exams. All right, so that said, we say that integers a and b are relatively prime if their greatest common divisor is 1. So a nice, very useful fact about integers being relatively prime is that they're relatively prime if and only if there are integers x and y, such that xa plus yb equals 1, so that we can write 1 as a linear combination of the integers. So this is an if and only if again, so that means we've got to do both directions. So for the forward direction, this uses something called the Euclidean algorithm that I don't really want us to cover in this class. I think we can get away with skipping that. So you can find that proof in the book if you'd like to take a look at that. For the reverse direction, let's suppose there are integers x and y. Such that xa plus yb equals 1. So then we want to show that they're relatively prime. So now we're also going to suppose d is a common divisor of a and b. So d divides a and d divides b. So our goal is to show that d has to be, well, plus or minus 1, and that'll mean that a and b are relatively prime since their greatest common divisor will be 1. All right, so then by the proposition that we proved a little bit earlier in this video, d divides xa plus yb, which is 1. So that means d has to be plus or minus 1, since those are the only integer divisors for 1. So that means that the greatest common divisor of a and b is 1, which means that they're relatively prime. So one of the most important uses of prime numbers is for unique factorization. So every integer n can be written in an essentially unique way as plus or minus a product of primes. So plus or minus p1 to the e1, p2 to the e2, up through pm to the em for some m, with positive integer exponents and distinct primes p1 up through pm. So when we say essentially unique here, this means up to reordering the primes. So this unique factorization is actually the reason that we don't consider 1 to be a prime, because we can multiply this thing by as many 1s as we want, which wouldn't change the value of n, but would sort of technically change the factorization, since we can put on like 1 to the 5th. That wouldn't change n, but it would sort of give a different factorization. So that's the reason that we don't want to let 1 be a prime number. So that's why that's excluded there. Oops, that's a line. All right. So then for proving unique factorization, so the proof is in the book. There's a lemma that is proven as part of that. So we're just going to prove this lemma, and you can look at the rest of the proof in the book if that's something you're interested in. So let p be a prime number, and suppose that a and b are integers with p dividing that product a, b. Then p divides a or p divides b. So at least one of those has to be true. So the idea here is that because p is prime, it can't be broken up into two pieces so that part of it divides a and part of it divides b, and once you multiply a and b together, you get all of p dividing a. All of p has to divide a, or all of p has to divide b. That's the only way it's going to divide the product. That's the idea there, but then to actually prove this is a little bit trickier. So first of all, let's write down what it means for p to divide ab. That means there exists an integer k such that k times p equals ab. And now we're going to look at two different cases here. So for the first case, if p divides a, well, that's one of the things that we wanted. So in that case, we're just done right from the get-go. So the interesting case that we can look at is if p does not divide a. So if p does not divide a, that's going to mean that the only common factors of p and a are plus or minus 1. So the only common factors of p and a are plus or minus 1, since the only factors of p are plus or minus p and plus or minus 1, and p doesn't divide a, so then the only ones in common are plus or minus 1. So that means that the greatest common divisor of p and a is 1, which then from the useful result that we had earlier means that there exists x and y such that x times p plus y times a equals 1. So now the trick to this one is that we're going to multiply this entire equation by b. So multiplying by b, we get xp times b plus y a times b equals b. And now, remember, way from when we started this, we wrote AB as K times P, and we've got AB right here. So we're going to replace that. So we've got then XPB plus YKP equals B. And now on the left-hand side here, we've got a P there and a P there. So we're going to factor those out and write this as P times XB plus YK, and that equals B. So we've got B times an integer, so XB plus YK is an integer. So then we've shown that P divides B. So in the case where P does not divide A, P must divide B. So that finishes our proof for this result. So moving forward from this, we're going to be going back to modular arithmetic, which we started to talk about on Wednesday. So using sort of how we've started to look at divisibility more rigorously and introduce prime numbers and see what that means in the context of modular arithmetic. All right, so make sure you answer the pre-lecture questions, and that's it for this video.